My name is Daniele Cortis. I'm from Italy, and I'm going to show you our research about joining dissimilar steels by means selective laser melting, material microstructure, and interfacial characteristics. So, just a little presentation of myself. I'm a mechanical engineer from INFN, that is the Italian National Institute for Nuclear Physics Research, and I work at a Gran Sasso National Laboratory that is one of the most biggest underground laboratory in the world. I am the head of design and I am lab department, and I also a member of our hub for additive manufacturing, material engineering and research. But here I am as a PhD candidate for my second PhD from a University of Roma La Sapienza. And this study has been done in collaboration with the INFN and of course Sapienza. So let's start to talk about the research. So a few years ago, we started to study the build with the classic SLM technology, that is one of the most common power by fusion technology application for metal material and additive. And we try to build some multi-material with this standard machine that we can buy on the market. Of course, a multi-material machine can be also a functional grade material that you can build to graduate the properties along one or other direction. In the market, there aren't well done or well robust machine that you can use or buy to build this kind of material, respect to, for example, FDM. So, but in the same way, you can use a simple, a standard SLM machine to build a simple multi-material in one direction, that is the building direction, of course, and graduate the properties. So, and here we try to study, to understand the behavior of a simple junction between the most common stainless steel that you can print with SLM, that is the HAESI 316, in this case low carbon, to another standard case hardened steel, the 16 manganese chromium 5. And here we study with metallurgical investigation the join with these two materials with optical and scanning electron microscope, and also we did energy dispersion spectroscopy together with an evaluation of the micro-hardness of the junction. So as I reported here in this picture, the most important part of the junction, of course, is this interface between the different steel. So, but why it's important to study this kind of application? Because in some application, industrial application or research field, as I know very well in my field of the basic physical research, it's important in some circumstances to have aberration of mechanical properties, like for example corrosion, in the same part of the structure of the component that can be subjected to a different working condition. So for this reason, there is the needs to develop some functional grade material, a complex structure with different physical properties that can be also thermal or electrical properties. And for example, overcome the actual limitation for the standard technology to join different material. For example, copper to steel, avoiding the brazing and the use of a third surface material between the main material that, for example, are copper and steel. So how we can do that? So we use a standard SLM machine produced by Sisma, that is an Italian company that now is under Trumf. And the machine is the Methint 100 PM-RAM, that is a specific machine developed for R&D. And the machine has a very fine spot laser, 30 microns, and a building fraction very small, about 10 centimeter for 10 centimeter. So how can a normal user build a 2D material along the direction or a functional grid material with this standard machine? So the procedure is very simple. Of course, first the user has to build the standard specimen to the standard component on the building platform, the machine. Then have to replace the powder material, realign the building platform with the character of the machine, and then build the second part above the first one. So it's very, very easy to say with this word, but of course it's necessary to tune, fine the parameter of the machine, especially in the interface, because for some material are not so easily to join together. In this case, we choose steel because there are a great affinity between, of course, this material, and so we can start to study the junction without other uncertainties. So in the process. As a reference geometry, we choose a tensile test specimen according to the ISO standard, because it's very simple to print a cubic specimen or very thin layer of two material. So we try to build something more big, more robust, that can be also CNC machine after the building process, also to understand the machinability of the two material joined together. Here you can see the process parameter. As you know, the main parameter for this kind of process are the laser power, the scanning speed, the layer thickness, also that the edge distance, that is very important in our case because we have a very fine spot laser spot. And of course, you can summarize all these parameters with the volumetric energy density, that is index for the evaluation of how much is simple, is hard to melt the power. And with this parameter setup, with this parameter, we can reach a relative density above 99%. And this relative density has been evaluated before with cubic specimen. For the records, we use powder supplied by the metals for printing company with grain size start from 15 to 45 microns. Here there is the specimen, one of the specimens that we of course build. And here I highlighted the junctions that we studied with this investigation analysis. As I said before, scanning microscope, energy dispersion spectroscopy, and also microarcans, of course. You can see the different steel because there is a very different color. So, okay, here there is the first important picture, the CM micrograph analysis that show that between the two steels there is no defect. So we can state that the junction is continuous and enjoy defect-free. So this is very important for example, the mechanical properties of the thermal conduction. Of course, there are some porosity microcavities in the bulk of the material that, as you know, is one of the main issues of this kind of technology. It's very hard to reach 100% of densities, because of course you can reach it on cubic on a very simple geometry, but when you build a very complex component, also it's very difficult to analyze it. Also, only with tomography, for example, computer tomography, you can see if there is other products in the components, but it's an issue that has to be studied and taken into account when you study the properties of a SLM component. Then here there are some pictures of the optical analysis where it's possible to see the microstructure of the two different materials. On the left, there is the magnetic structure of the steel case hardening steel. And as you can see, the boundary of the laser track or the boundary of the pool are not visible. And also the image confirmed the presence of microgravities and porosity as we see before. This banatic structure is sometimes common with the Selema process in respect to the Martensidic structure, of course, because probably the solidification probably not follow exactly the standard plot graph that we know. On the right, there is the austenitic structure of the IEC 316. And here, on the other hand, you can see the structure of the grain, the multiple laser tracks, and so it's a very more clear figure that confirm, of course, the literature of this material that is one of the first printed with this technology. Then also here, always with optical analysis, there is the image of the junction. So the junction is about 200 microns thick, and you can see here some intermixed phase between these two materials. And these intermixed phase are generated by probably a variation of the surface tension. And this variation, of course, of the surface tension promotes the generation of mass flow, also known as Marangoni effect convection, that also is an effect that can enhance the bonding between the two different materials. In this case, of course, between these different steels. So the thickness of the junction confirms probably the depth that you have when a laser pass over one layer above one other layer, that usually is 3 or 4 layers. So we print these components with this pattern with a layer of 40 microns. So 4 or 5 layer is the depth that can reach the laser track. And here there is the EDS analysis, and the EDS analysis confirmed the good interfusion between the steels and, of course, the different elements, manganese, nickel, chromium, and iron, of course. And also here you can see the Marangoni effect described before. Finally, we did an evaluation of micron hardness with the Vickers load test, and with this plot we can see a rapid variation of micron hardness. Of course, micron hardness is a very complicated test in this case because you can find some porosity under the surface of the specimen that change, of course, the value that you can measure. So talking about the two different steel, we find that for the steel case hardened steel, we find a value of hardness slightly below the value that we find in literature. On the other hand, for the hazy, the value that we find is slightly higher than the literature. Of course, these values are influenced by the cooling, the speed of cooling that for SLM is very high. So 10 to 6 or 10 to 8 Kelvin per second. That is influenced, of course, the overall mechanic properties. Finally, the conclusion of this work, so we can see that it's possible to obtain very good joining between two materials, free of defects. And as I said before, the cooling rate is one of the main factors that can influence the structure of the junction of the material and can generate some internal motion of the melting pool that is very hard to study or simulate for a single material. And so for two or different material is too high. And this is, as I said, is a preliminary study. We are trying to judge some other material for physics purpose and not only. And we are very interested in this kind of opportunity that a standard SLM machine can do to us or to other users. So we are trying to, of course, investigate the mechanical and thermal properties. And for example, we choose a specimen, a tensile specimens to characterize, in this case, before do some mechanical tests, because in this case, we are sure that the junction is made correctly, and so we can do some mechanical tests without any uncertainty, and so evaluate the classic mechanical properties, so the yield, so on. I'm here if you have any other question, and thank you for your attention.